Okay, so this is Bohr's vision of the substantiated with some elegant mathematics as well. Yeah, the paradigm of a um, planetary system with orbitals, and then electrons were required to be on these orbitals, but no other place. And see, this would fit in nicely with Rutherford's model as well, where Rutherford was saying that everything was mostly empty space. So basically, then between the orbits would be empty space. And because the orbitals are getting bigger and bigger as they go out, it could put more electrons in there. So the innermost one was 2 electrons, then it was 8, then it was 18, and it kept building. Now, there were some issues with his model. And whenever you take something and then change its direction, it requires a force. When you take physics, or if you take physics, there's an equation called F is equal to ma. F is force, m is mass, and a is acceleration. So because this is curving off of a non-straight path, it requires force to keep it on that. And since the atom is just sitting there, there's no force that can feed that directional change. So what happened, the electron just would basically spin out into the nucleus. And they couldn't explain why electrons didn't do that. So they came up with another model that answers all those questions. And that's the quantum mechanical model. And again, in 1920, that's when it was accepted. Okay, on the periodic table, we talked about these guys being periods. And there's another name for them also. It's called a shell. And those shells corresponded to Bohr's orbits. Okay, we found that the orbitals were actually split up into suborbitals. Now, on the innermost one, there's no split up. But the next one out, it's really composed of 2 orbitals, suborbitals. And this one out here is 3, etc. So we get over to our periodic table. So that's shell number 1, or period 1. And notice it only has 2 electrons in it, or 2 elements. Period 2, it's got 2 elements here and 6 elements over here on the right. When we get to 3, remember 3 I said was 18. The problem is, if we look at this, on period 3, or shell 3, we've got not 18, we've only got 8. So what is going to happen is we're going to pick up the other 10 right there. So now we have 2, 12, 18. So that would be represent Bohr's third orbit. These elements are going to be represented in those orbitals. Now I'm talking about electrons in the orbitals. There's a term called orbits. That's what Bohr used. Quantum mechanics uses orbitals to distinguish them for not being a planetary model. It's a scatter plot. Remember I gave you the analogy of the smokers at Rayleigh's? We had the cigarette butts by the one door. We don't know how they got there, but we know where to find them, right by the door. We also don't know who the original smokers were, Rayleigh's employees or customers. We don't really know. All we know is where to find them. That's the quantum mechanical model. We know where to find the electrons. We don't know how they got there. Where Bohr says, well, it's in a defined orbit. And I talked a little bit why his model doesn't answer some questions. Okay. So a shell is the whole thing. Subshells are pieces of the shell. So this would be a subshell, and that's a subshell. And we're going to name this first subshell as S, and the second one over to the right as P. Okay, and we're going to also number it. So because this is in shell 2, this is going to be 2s block, and this is going to be a 2p block. Now, for period 1 or shell 1, it only has an S. And this is also S over here. Now, one of the things you're going to learn how to do is identify, for example, we look at lithium. Lithium has 3 electrons. Its atomic number, not its atomic mass, atomic number is 3. It means it has 3 electrons, 3 protons. Okay, so you need to identify where those protons are located. Well, the most stable shell is 1. That's the inner orbital. So that's the most stable orbit. Those are going to fill first. We're going to put 2 electrons there in that inner one. And then we have 1 left over. So that's going to come out to here, to shell 2. Okay. So if we were going to actually write down the electronic configuration for lithium, it would be 2 electrons on shell 1 and 2 electrons in subshell S. Okay, that takes care of 2 electrons. And then we have 1 in subshell S on shell 2. So the electronic configuration for lithium would be 1s2, 2s1. Yeah, I'm going to talk about that in a second. So the first number is what shell it is. The superscript is how many electrons are in that shell. and that's the subshell name. So there are three parts. What shell are we on? Which is what period? What's the name of the subshell? How many electrons are in that subshell? Okay, so basically what you do is you start from the beginning, not start from the beginning, the most inner part of the atom, and start filling it out as you go out. Because the closest orbit to the nucleus is the most stable, because the nucleus is positive, the electrons are negatives, they want to attract. So that's why those are more stable. As you keep going out, further and further out, it becomes less and less stable. So those fill last. Okay, so that's lithium. Let's do one, like let's do oxygen. Oxygen has 8 electrons. So what does the orbital diagram look for that? Well, we have the shell number 1 going to start to fill, and it's going to fill up with 2 of those electrons. And we still have 6 more to go. So we're going to start on shell number 2. You can only put 2 electrons in shell S. So that takes care of another 2. I'm going to go over here to the next subshell, which is labeled P, and it's 1, 2, 3, 4 electrons in. So we have 1s2, 2s2, 2p4. And when you're done, you should be able to add up these electrons, and they should be equal to that. All we're doing is we're taking the 8 electrons that oxygen has and subdividing those electrons into orbits or orbitals. We're talking about quantum mechanics. Now, remember when we were doing Lewis diagrams, how many electrons make up a bond? 2. We have 6 to account for. So how many orbitals are in the p block? 3, because 3 times 2 is 6. So there's 6 places to put electrons in the p block. And we've taken 4 of those places. So we can further subdivide the p subshell into individual orbitals. So what it's going to look like is those are the 2 electrons that are in the 1s2 subshell. Okay, and those are represented by these arrows. Notice they're opposite. The reason why they're opposite is another thing that quantum mechanics came up with is electrons are magnetic. So it's like 2 magnets together. You put north to north together, they don't want to go. You flip it around, they attract. So that's why these are like this, and it's called spin. So the spins have to be opposite. Spin represents the 2 electrons that are in 1s2 subshell. And that only represents 2 electrons out of the 8. So we need to start doing some more here. Okay. For the 2s2, we're going to be putting 2 electrons there as well, opposite spins. However, down here we have 3 orbitals, because we have to account for 6 possible electrons. So these 4 electrons now are going to be spread out over those 3 orbitals. Now, there are 2 ways to put them there. And one way is more stable than the other way. So let's represent the 2 ways. Put those in. One way is we fill up the first one, 2 electrons, then we fill up the next one with 2 electrons, and that takes care of the 4 electrons, leaving 1 orbital empty. The other possibility is to do it differently and fill all the orbitals with 1 electron first, and for the 4th one, we pair it up then. Guess which one's more stable? Who thinks the first one's more stable? Okay. And the rest of you, okay. Remember we talked about, I almost, I was about to say, remember we talked about reaction stability? It's my other class. Okay, nature likes symmetry for stability reasons. Which do you think is more symmetrical, the left one or the right one? Okay. This is sort of lopsided, or this one's more spread out. Now remember, electrons are the same charge, so they like to be as far apart as possible because they repel. So by doing it this way, we've got the best separation between the electrons. Number one. Number two, it's more symmetrical than this one. So as far as stability goes, this is more stable. So that's the preferred one. And all the math that goes along with this. When I took quantum mechanics, that's all they covered in 1 quarter at Davis. All we talked about was quantum mechanics. And the reason why you have to take calculus if you're a chemistry major, and the reason why you have to take differential equations as a chemistry major is because of physical chemistry. And one of the classes is physical chemistry is quantum mechanics. That's the hardest class I've ever taken, this class. You know, I was a math major too, so the math didn't scare me at all. It was just the complexity of these equations. I mean, they were like this long. They're doing triple integrals and all this stuff. It's pretty wild. Okay, so what we're doing is if we have multiple electrons in a subshell that has multiple orbitals, suborbitals like this, we're going to feed them like, we're going to give electron to each one first, then we start pairing them up. Okay. Yeah. Yeah.
Is closest to the nucleus, right?
Correct.
So how come the one on the left isn't more stable? Because it doesn't that one show more electrons closer to the center? Or am I understanding it wrong?
These are equal distance from the nucleus. Okay, and those 3 orbitals correspond, they lie along the x-axis, the y-axis, and the z-axis. So that means they're the same distance to the nucleus. Okay, so the quantum mechanics has 4 variables. Variable number 1 is the shell. Variable number 2 is the subshell, how many subshells we have, how many electrons can fit in there, and then also how the electrons are distributed. And again, they're randomly distributed. If you had a super microscope, you could actually look in there and all you'd see is electrons darting about with no perceived movement. There's something called a uncertainty principle. And that means you cannot know either the direction or the velocity of an electron. You know electrons there, but you don't know much about it. Okay, now this is your book goes into more detail than this, but this is really the main thing I want you to feel comfortable with is getting down to this level here, drawing in the orbitals and filling in with the appropriate number of electrons and being able to write out an electronic configuration. Now, there are four things we can talk about in terms of stability. Okay, the first one is full shell. If a full shell, if you have enough electrons to fill the whole shell, that's the most stable. And that's why the noble gases are stable. Because if you look at the electrons, let's look at neon. Okay, so neon has 10 electrons. Okay, so we start filling them, innermost ones first. So we're going to have shell 1, subshell S, 2 electrons there. We continue filling these now until we run out of electrons. Shell 2, subshell S, 2 electrons. And then we have the P subshell, still in shell number 2. So remember, the shell is made up of subshells, except for the one. That is both a full shell and a full subshell as well. Okay, so the next down, now this is going down the list here and decreasing stability. Okay, so a full subshell is stable, but not as stable as a full shell. Then we have a half full subshell. And then lastly, we have nothing. No. And these all have to do with symmetry. The full shell is the most symmetrical. A subshell full is also symmetrical. Half full is symmetrical. And if it's none of these, I just put a null set there. It's the least stable. So let's look at going back to oxygen. Okay, so on the rules here, full shell, is oxygen have a full shell? Let's look at shell number 2 now. Not that. Okay. Does it have a full shell? No, because we have 2 spots left over. So it's not a full shell. Is there a full subshell there? Shell number 2 now. Is this full? Yeah, no more room in there. So it's full. Is this subshell full? No. Has 2 places left. So oxygen likes to form a -2 ion. Remember, -2 means 2 extra electrons. Guess where we're going to put them? Right here. Now, oxygen -2 has a full shell. So it went from a not full shell, a not full subshell, to a full-blown shell. That's why it likes to gain 2 electrons. So the ion oxygen forms is going to look like this. That's going to be like that. So full shell, full shell. So that's why, number 1, the noble gases are so stable, full shell. Number 2, when elements that normally you don't find them by themselves, the reason why they form ions is so they can fill up those orbitals or take electrons away. A +2. Okay, this is oxygen now. +2 means it would lose 2 electrons.
Oh, okay.
One thing you could do though, if you lost 1 electron, then you'd have a half full subshell. But this is more stable than this. And taking 1 electron away is more stable than this. This is like the worst possibility when you don't have any of those filled or half filled. Okay, so notice these 2 are exactly the same. Neon's electronic configuration and this ion of oxygen are exactly the same. So this is, it's called isoelectric. So that oxygen ion is isoelectric with neon's electronic configuration, hence the stability. So that's why ions form, is to look like a full shell. Let's look at fluorine. How many electrons does fluorine have? 9 electrons. Nine electrons, okay? We've accounted for 4, that means there's 5 more. Now let's draw the orbitals in now. 2 electrons there, 2 electrons there, 5 electrons here. It's not a full shell because you're missing an electron here. So how can we get a full shell? Yeah, acquire one from somewhere. It goes right there. Then it's isoelectric with neon. Keep going back to those noble gas configurations. Yeah,
think the P shell period 2 going to be isoelectric with neon in its most stable form?
yeah, after it loses or gains electrons. Yeah. And that's the driving reason for why ions form at all.
And that's the same for every period on the table.
Yeah. It gets more complicated when we get to period 3, however. What was your question? Not two different elements. If you're just looking at the bare element, a neutral element, they have unique configurations. But if you gain some electrons or lose electrons, then it's going to be isoelectric with something. So if you lose one electron, like with oxygen, you're going to have oxygen plus 1. So it's going to be isoelectric with nitrogen. Yeah. And you need to look at the charge of the ion. That'll determine how many electrons you're going to put in there. And you start with the 1s's, then the 2s's, then the 2p's. Okay, so let's look at something in let's look at tell you what, why don't you as a little exercise right now, at your seats, write the electronic configuration for phosphorus. Phosphorus is right underneath nitrogen. Right here. So you have 15 electrons to deal with. Everyone's writing the electronic configuration for phosphorus. And it's optional to do squares or circles. Yeah. Yeah, I don't know. When I first learned this back in high school, 1966, I learned circles. So I've been doing circles ever since. But you just need something to represent the orbital. That's all it is. That's why it doesn't matter.
Circles, square.
Yeah, exactly. Her comment was the book uses squares rather than O's or circles to represent an orbital. Okay, so let's go ahead and do this. Okay, it's got 15 electrons. We have to find places for those 15 electrons. So we're going to do 1s2, 2s2, that takes care of 4 of them, 2p6, that's 10, 3s2, and then how far over is phosphorus? 3. So we have 2, 2, 6, 2, 3. That adds up to 15. Now, if we look at the orbitals, so which do you think is more stable in a neutral, oxygen or phosphorus? Why? That's right. Why? Yeah, this likes to gain 3 electrons too, but the reason why this is more stable than oxygen, remember oxygen has an extra electron, which messed this up. This is a half subshell, and half subshell is more than into the null set. So that's why phosphorus is more stable than oxygen, because this guy is half full.
Hold on. 2 circles, 1 full, 1 half.
I'm not sure the question again.
So like for the.
Yeah.
It'd just be the 2 circles and then just full 1.
Because like that.
Do we have to have the 3 circles?
Yes. Yeah. Yeah. You always have to have 3 for peace.
Oh,
Okay. No exceptions. And then the way we're going to fill it is we're going to distribute them first, 1 in each one, just to maximize the distance between the electrons.
Yeah.
And then see this one, they're shoved together.
I was picturing 2.
Does that make sense though? Oh, you have to distribute it. We're going to find these have 5 orbitals. Okay, so if you look at nitrogen, nitrogen's above phosphorus, so it has 7 electrons. So that's nitrogen. Now, one of the reasons why phosphorus, remember, phosphorus is in the same group as nitrogen. Remember, we talked about groups having similar chemical characteristics. This is why. It's because this is the valence electrons here. Those valence electron configurations look just like these valence electronic configurations. That's why the chemistry is the same. So again, valence are the outermost electrons. What that means is the highest shell number. So the highest shell number with phosphorus is 3. So you look at only the 3s for valence. This is the highest one over here, so you'll look at the 2s. Then when you look at them, they're exactly the same. So if the valence electronic configurations are the same, then the chemistry is the same. So what do you call these electrons then? Those are core electrons. Now, if you look at the electronic configuration for the core electrons here, it's a full shell. I'm just talking about core electrons. That's why core electrons are so stable. Full shell. Okay, so are there any more questions about this? Because I'm going to jump to one that's in the 4th shell here. All right, so let's look at iron. Iron's got 26 electrons. I don't know how I came about 25. Anyway, 26 electrons. Now notice this is the 4th one down. That means it's shell 4, except for the transition metals. They are part of shell 3, but they don't fill until we fill these guys. So remember I said the first one was first orbital shell, 2 electrons. The next one is 8, 2 plus 6. And the next one I said was 18. Okay, so this thing's supposed to hold 18 electrons. But if we just look at the placement of the periodic table, there's not enough room for 18 electrons. So what happens is it's like this. So the 3rd shell maximum is 18. Okay, so we're looking at iron now. 26 electrons. And it's located on the D block, as in dog. So 26 electrons. We're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How far in is iron? This block here. 1, 2, 3, 4, 5, 6. So let's add these up and make sure that it adds up to 26. Okay. 2 plus 2 plus 6 is 10. Plus 2 and 6 is 18. Plus 2 is 20. 6 more is 26. So what does the orbital representation look like for that? Now for D orbitals, there are 5, because it can hold 10 electrons. There's 2 per orbital, so that's 5. And we have 6, so we're going to go Now, you normally don't find iron metal naturally. The early people got iron from meteorites. And this is why this electron here is messing up this subshell. So what could we do to improve the stability of iron? Lose this electron here, and that'll make it a full subshell. So that's why you find iron in nature as an ion. It's called rust. Now you can convert rust to metallic metal by applying that electron again. Okay. So as far as blocks of electrons go, let's do a different color here. So those elements contain on their outermost subshell s electrons. So s electrons, s electrons, s electrons, s electrons. Okay. The next one are the p's. And we have d's. And guess what? Down here we have f's. And there are 14 possibilities with the f's. Now you're going to go into these in 1A, 3A, and possibly 2A. For sure in 1A and 3A. And these, interestingly, are 2 down. So these guys, the first row of the F's is shell number 4. So as you're going across, filling in these electrons, as soon as you hit this inner transition group here, you're going to drop down 1 and you're numbering. These are part of the shell above. And the reason why it's this way is because these guys are more stable than these guys. Hence, it fills first. That's why the period is set up this way. The periodic table one. Okay, so we're not going to do F's in here out of the scope of this class. You are going to have to do D's though. Okay, so let's do another D. Let's do let's do selenium right over here. So that has 34 electrons. And then selenium is 1, 2, 3, 4. So that'd be selenium. Now, depending on what book you're reading, some books call these guys valence as well. Other books call it core. Because going back to what I said earlier, you look at the highest shell number, which is 4 here. So these for sure are valence. And the question is, what about this guy? And for our class, we're going to call it valence. Yeah. I'm sorry, say again. Well, valence can be full. It's just the outermost electrons. And does it fill up the whole orbital? If yes, then it's super stable. If not, it's some subset of that stability. Yeah. Because these fill in, when you're putting electrons in an atom, the most stable orbits are filled first. Okay, once it's full, then you go out to the next one. Once it's full, and what happens is the S's are more stable than the D's. So that's why it fills first, then you go to the D's. It's
Like, how do we get the order?
Hmm?
How do we get the order of like the 3 F's, 3 P's? Yeah, all of those. How do we know what comes next? Which ones?
okay. So let me show you a way one of my students invented back, oh, it's about 15 years ago now. She ended up being up in Tacoma Community College has a program where you can have it's like a TA or teaching assistant who's had the class before. They call it at Sac City, they call it PALS. And I don't think they have that here. But anyway, what she would tell her students that she was tutoring, she would call it a journey. And this is what she did. She said, okay, let's look at selenium again here. Okay. So if we were to start at the top left of the periodic table on a journey, as we went along, we write down the electrons we run into. So if we start up here, that's shell number 1. So we're looking at 1s1 and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. As long as you know the block names, if you know the block names, and you just, and most of the time, now your book does it differently. It has this diagonal diagram and how this fills, and you have to memorize that. Well, with my method, you don't have to memorize it, as long as you got a periodic table and you know the block names. Just as you travel along to get to your element, just write down everything along the way. And that's what, and it works every single time. Yeah. 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 So his question was, is the pattern always the same? Yes. And eventually when you get down here, you need to throw in some F's. So this is the way um, this here is the way your textbook has to remember it. 1s, 2s, 2p, 3s. Notice instead of having so after 4s comes 3d, then 4p, then 5s, then 4d. And this is to me more confusing than just doing it along the periodic table. But the reason why those D's are goofy and the F's are goofy is for stability reasons. Because the more stable orbits fill first. So if the 4s is filling before the 3d, that's because the 4s is more stable than the 3d. Okay, and one other thing. Remember we talked about how to fill the electrons if you have multiple orbitals? This guy here came up with that rule. You fill them singly first, then you start pairing them up. What's more important is how to configure them rather than remembering Hudd's rule. Okay, let's see. I wanted to talk about, let's see, there's no good picture in here of it. All right, let's look at iron again. Sometimes they'll say this is the ground state configuration for iron. Ground state. That's the most stable configuration. Now, one thing you can do, if you took this iron and zapped it with some energy, this electron here could go to another orbit that's empty. And that would be called an excited state. Unstable, though. What would happen, it would want to return back to the original. So you have ground state, excited state. Fluorescent lights. They used to call them neon lights. The reason why they call them neon lights is because they're filled with neon gas. And if you look at the electronic configuration for neon, which we did earlier, it doesn't matter, by the way, which side the up arrow is on. You can put the first one down as long as they're opposite. That's the main thing. Okay, so this is the orbital diagram for neon. Now, what happens with neon? Now, neon is particularly stable because it's a full shell. Full shell, very, very stable. So if you have neon and you zap neon, it's going to take one of these guys and put it into an empty orbital. And what you're doing is you're destabilizing neon big time. That's why it requires energy to destabilize, because it's very stable to start with. And then what's going to happen is it wants to become stable again so that electron there returns back to its original place. And then the energy it gives off when it returns is what we're seeing, light, because the energy is in the visible spectrum. Lasers work this way, fluorescent lights work this way, LEDs work this way. But it requires energy. And the reason why it requires energy is because we're putting it in a more unstable place. And it wants to return back to its stable place. And when it does that, it gives off energy. Okay, so this is a very different way of looking at an atom. But you can use it to explain why ions form. You can explain it why when you excite an electron in a stable configuration, it requires energy because it's going to more unstable configuration. And then that electron wants to return again. When it returns, it gives off energy. So let's do a couple more things. What I wanted to cover today was this, no more than this. This is a lot. I want you to be able to write down to, this is shell 5 going across here, and this is 4D. You should be able to write electronic configurations for those up, okay? We're looking at down to shell number 5. We're not doing any Fs, but you feel very comfortable writing and don't worry about those below shell 5. So for practice, why don't you do oh, I don't know. How about try 10 at your seat. Now you're gonna have to account for 50 electrons. Hmm? 10, yeah, 10. SN. It's not Colorado. Oh, so yeah. How was that shooting resolved in Sacramento? There was another big shooting in Clinton, New Jersey today. It was on the news all over the place. Yeah, on NBC, CNN, stuff like that. I don't look at the local news. That's why, I look at internet news. So. Yes. Yeah. That's another thing that the quantum mechanics came up with. Yeah. See, Bohr said it's okay to have them all in one orbit. The quantum mechanics says, no, 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 no. It's the other way. So this makes sense?
Good day.
Good.
See you in a couple weeks.
Yes. Don't forget, we have a week off next week. Oh, yeah, yeah. I decided to give you guys a break on your last test 2. Most of you missed points on the Lewis structures. So if you would like to correct your tests and resubmit that, I'm going to have an assignment where you can submit that. I'll give you, assuming they're all correct, remember there's 3 alternate structures for that formula, I'll give you half credit. So it'll go from 12 to 6 points. If you'd like to do that. Did you get it right? I tell you what, why don't you correct your tests? Okay. So her question was, well, I didn't miss the Lewis structures. I missed this other. And you're probably thinking that's not fair, right? So yeah, just correct everything on your test. And then resubmit your tests though. And show me your corrections on your test. I want to see why you missed it. Yeah. Yeah. Just like a lab. And in fact, I'm going to create the assignment right now. What's your name? Oh, sure. Yeah, you can get yours back. Go through the initials here. What's your name?
Yeah.
Here you go. Yeah, I was gonna, before I forget, I was gonna do the assignment for yeah, only I don't want you to look at the scores though.
That was me.
Oh. You can look at that one then. What's your initials? Huh? Uh-huh.
Like the poster?
Yeah.
Can I email you? So I just want to make sure that.
Oh, yeah, yeah, for sure. Yeah. Yeah.
Thank you.
I can usually make something out of whatever your interest is. Because chemistry isn't everything. It's oh yeah. What's your initials? I was trying to convince my friends to go to Paisano.
Yeah.
They want to go to Vince's instead.
Oh.
Yeah, but they definitely want to try it though.
Yeah, you're getting closer to going.
I also looked on your menu. You don't have eggplant parmesan on there.
We don't.
Vince,
We have chicken.
is the chicken parm with breast? How was that?
A lot of people, I'm not a big fan of it, but a lot of people like it.
I hesitate on ordering chicken
Yeah,
because the rest is always overdone and
Oh.
it's dry.
I get it.
Because at home, I'm real picky about
Yeah.
the temperature and it comes out really good,
Yeah.
but restaurants, you know,
Like, you never know. I'm the same way.
What's this name?
metals.
Yeah.
Well,
But
these,
I don't think you took points off.
yeah, I didn't take points off. Let's see, what did you get? One, yeah, I just did that one. See, these are separate molecules. One is, they needed all
Supposed
be,
to connect, right?
yeah, exactly, yeah. But so you can get 5 points there.
Okay.
I'll bring it up to, I don't know, higher than that.
Thank you.
Sure.
This one has to be 5, not 5, it's 4D, right? Or 5D.
Yeah.
And it's 2N, yeah,
Correct? So
Mhm.
it's 4D.
or D, yeah.
Because she thinks it's 5D, so I'm gonna put it.
Oh, yeah,
Then it's dry left, right?
no,
He's not a dry. No. Okay.
it's on hydrates.
Okay.
It's a pretty short write-up. You should be able to do it in pretty fast, so.
Okay.